Hello everyone, welcome to this talk. I'm Guercio, last year PhD student at the University of Nottingham in the UK. So today I'm going to talk a bit about new high-strength aluminium alloys specifically designed for L-PBF, as a lot of people here. So when we are talking about printability in L-PBF, we refer to all kinds of phenomena that regard the interaction between a melted track, a substrate, partially melted zone, and also within the melted track itself, the behavior of the liquid, the mushy zone, and even a bit of evaporation with regard to Keogh. So all these interactions may cause different effects in L-PBF, as we all know, which mainly can be subdivided into two classes. We have porosity and we have cracks. When we talk about porosity, of course, we have gas pores, lack of fusion, and Keoghs, and all these types of porosity, we know roughly the trend of that as a function of process parameters. But when we're talking about cracking, especially hot cracking, which is quite detrimental in aluminium alloys, we don't know the effect, how is it controlled in the L-PBF process. We have some hints, some idea, but actually we don't know how cracks changes as a function of process parameters. But also from a material point of view, this is quite interesting, because of course, hot cracks, as you can see, and cracks in general are very, very detrimental for high-strength aluminium alloys. So I started working with 2024, quite known aluminium alloy, a couple of years ago, and we studied the cracking behavior of this alloy, and we found out that there is not actually just one cracking mechanism, but there are at least two of that, at least in this class of materials. And the cracks that you see here microscopically, they are cold cracks. Cold cracks are thought to propagate from hot cracks directly. And this affects, of course, the consolidation of the build. So when we take a deep look at microstructure here, what we can see is that apart from these macroscopic cracks that can be easily seen, there are plenty of these very, very small cracks which are randomly oriented, which are thought to be hot cracks. So I selected this image because it was near a cold crack as well, but these hot cracks here can be found also in regions of the microstructure far from the cold propagated cracks. So it was crucial at the beginning of my research to isolate these features and to understand what are the microstructural chemical features that are affecting this nucleation. So what we did is a 3D reconstruction of a hot crack tip with specific aim of understanding what is grain orientation to the left and to the right of the cracks, but also what is chemical profiles found at the cracked surfaces. So when we remove the L-PBF, what we can see is that hot cracks are found, of course, at grain boundaries, and we were aware of that, but also we can find a peculiar segregation of alloying elements. Specifically, this alloy is copper-rich, so what we can see here is the presence of copper-rich alloys near the hot crack tip. And we are 100% sure that this is a hot crack, also because we can see some oxidation, which is known to be a clear effect of a crack formed at high temperature. So once we understand this, of course we need to collect everything together and explain it, say, what are the factors affecting hot crack susceptibility of an alloy. And there are many factors, of course. Of course, process parameters are one of these, but when you're just talking about the material, we can subdivide these into many classes. So the first that I found that was quite peculiar is the intrinsic hot crack susceptibility of the material, which is ultimately given by the slope of the solidification path towards the end solidification. And this was proposed as a criterion by Hu a few years ago. It is widely used in the L-PBF community to assess the hot crack susceptibility of a given material. But there is actually more to this, because what we found out investigating also process parameters and stability of hot cracking as a function of process parameters is that, with regards to, there are other factors. One of these is mushy zone size. The concept is that when you have a larger mushy zone, it's harder for the liquid to backfill the crack. So you have a higher chance to nucleate hot cracks in these regimes. But this is, as far as material is concerned, we can try to map this just with solidification range. And then, of course, there are microstructural features such as segregation, and grain boundaries, texture, and grain morphology, which we all know that acts on grain morphology is something that works. So, at the beginning of my PhD, I said, I don't want to do this, I want to investigate something new, so I start on pure columnar microstructure, but trying to avoid hot cracks. So what I thought is that, okay, we can do a design map based on these two parameters, just to map the overall constructibility of the material. So of course, usually high-strength aluminum alloys have high ACS, low and high solidification range. Of course, we are there, and we want to be in a region close to the origin of this chart. So when it comes to okay, now we understand how to map these changes as a function of ultimately the composition. But we also wanted to develop an alloy design and development process without powders. So what we did is, first of course, design of the compositions. So we started with aluminium copper binary because, of course, it has great strength, great treatability, widely used in the high-strength aluminum alloys. And then we added nickel as a third element in our ternary. This for two reasons. One is to maintain a degree of mechanical properties, and just by textbook at the beginning, and then also to simple fact that also in a binary, when we compare the binary aluminium nickel and aluminium copper, aluminium nickel has a eutectic at a higher solidus temperature. These automatically, just by textbook, reduce the solidification range. And then we compute solidification paths via thermocoke, and we of course we evaluate the HCS, the slope at the end, and solidification range. Here we also validate the solidification path, doing an investigation of the phases present in microstructure via XRD, so that we know that the phases that we put in solidification path during cooling are the exact phases that we found actually in the microstructure. Then we go into the arc melter here, and we produce different compositions. Specifically in this talk, I'm going to discuss 10 different alloys, labeled alloy 1 to alloy 10. The concept behind this is a progressive change and increase of alloying elements from 1 to 10. And then we need to simulate the L-PBF conditions. We do this, if this is our arc melted button, we do this by remelting of the top layer of the button. This gives us also a good insight about cooling rates variability, because of course the button here has a lower cooling rate than L-PBF, can reach also 10 to the power of 7 Kelvin per second. And to validate and have an idea of the mechanical properties, we do hardness measurement, both in bulk and of course on the remelted layer. And here you need to be very precise to go spot on the melt pool and not put the indents between the melt pool and the core, so that we are 100% sure that these are the properties found in the remelted microstructure. Okay, so from alloy 1 to 10, we have a lot of solidification paths, of course, and what we can see is that when we increase the alloy number, so when we put more solids in our alloy, we have a progressive change of these curves towards lower solidus temperature and a higher, lower liquidus temperature and a higher solidus temperature. And we start to see with alloy number 9 and number 10 also first precipitation of aluminium 3 nickel as a primary phase. Then of course we compute HCS solidification range, and we compare them to data that we already know of 2024, and also modification of 2024 also with this alloy design approach, which gave us very, very good results, but we just wanted to be a bit more sure about the design map, because we saw a bit of variability as a function of process parameters. So we wanted to say, okay, we can bring these as fast and as high power as we can, so that there is industry relevant. So we are here in this zone at the moment. So we discard the first 3 compositions, and we're working in this area only. So okay, for the rest of this talk, I'm going to compare 2024 with our custom alloy. So 2024 is an alloy hot crack susceptible, but if you want to isolate this, a very, very good way, in my point of view, is to produce the alloy without cracks, and you can do this acting on process parameters. It's not easy, but you can do it. And then remelt the top surface with standard parameters, there are, of course, can produce hot cracks, as you can see here. So what you can see is the presence of a remelted layer characterized by a lot of cracking and a crack-free microstructure in the core. When we do this with our custom alloy, of course the core is different. One is L-PBF material and the other one is melted material. But the remelted layer has very similar microstructure in terms of cell size and of course also molecular arrangement, of course. But what we can see here is that there is presence of a crack-free microstructure in both the remelted layer and the core. So we take a look at the interface between the remelted layer and the core. We can see a progressive change of the microstructure towards a very, very refined microstructure in the remelted layer. Here, cells are around 300 nanometers in size, so they're very small. Then we measure the hardness of this bunch of alloys, and what we saw is that when we increase the alloy in number, we reach very, very high hardness values. But most importantly, in our point of view, is that you reach values that goes way beyond standard age 2024 and L-PBF of 2024. So our comparison is proved to be effective. So we select this alloy here, which we call AAMS22, just because we were afraid that this alloy would form not hot cracks, but cold cracks during printing because it's too brittle, because it has huge hardness. Okay, so when we print 2024, as you can see here, when you compute relative density in the high power, high speed regime, you have very good consolidation, because this is the kind of microstructure we have. There are a lot of cracks, of course. But when we order our alloy, we printed our alloy, what we found is that there is great stability as far as consolidation is concerned, and with a speed which is 10 times faster, you can achieve way better consolidation without cracks. Okay, then we investigated the microstructure because I wanted to have a look at this L-PBF microstructure. This is part of our still ongoing work, but what we can see is that, of course, we see the metals, still don't have EBSD data, but you can see that columnar grains can be found from the outside of the metal towards the core. So this is technically still a columnar microstructure. There may be a bit of refinement due to the solids, but it's technically not grain refined. And then when we see the metal boundaries here, it's a bit easier to see cells with a Fag SCM, for example. And what we see here again is this very small cell size, which is thought to be the main reason for the strengthening of this alloy. Of course, we wanted to double check the phases, and these are the same phases that we find in the remelted buttons. So this is quite a complex alloy, because of course we cannot see, of course, the FCC. We can see famous theta phase, but also we can see two different aluminium nickel compounds and a ternary compound. And all of these can be somehow spotted here with different intensity of the white phases, but of course this needs more analysis to be precise. So this complex, very complex ternary alloy showed very great strength as far as UTS and yield are concerned. But in the unstable state, we show a lower conductivity with respect to, for example, 2024 steel L-PBF. So to conclude this presentation, so our custom alloy show unique microstructure achieved due to a L-PBF oriented alloy design approach, which of course is crack-free, no grain refiners, and we avoided at all the use of powders in the alloy design approach. Next, of course, we want to know why these alloy cracks at fairly low values of ductility, performing treatments to improve this. Thanks, and I'm here for your questions.